Welcome back. And as I mentioned last time, we're going to continue with the process abstraction by talking about threads. Threads extend the process abstraction to allow us to use multiple cores or CPUs concurrently. In the subsequent lectures, we're going to talk about the tools we need to communicate between these threads and build off the work that we're doing today. So let's start by thinking about what is a thread. So last time we left off by talking about a process, and a process is an instance of a running program. It's got all its code, the data, the file descriptors, CPU registers, and stack, and it has a single execution context. It has a single program counter and a single point in the code where you're currently executing code. Threads extend this by allowing us to have multiple contexts for execution. It allows us to execute different functions at the same exact time on different CPUs or cores. In a multi-threaded program, unlike a multi-process program that we mentioned at the end of last lecture, a multi-threaded program will share the code, the data, and all of the file descriptors within the same process. Only the local variables and the register state are unique to each thread. Why is it that we want to use threads rather than processes? The first two important reasons are that threads are a much lighter weight process. It's a lot easier for us to create threads in the operating system, and they share all of the memory and file descriptors, so it's easy to communicate within the same process. They allow us to use multiple CPUs or cores, as I mentioned, and they're also a really efficient way for us to overlap I/O operations and computation. If you can think back to the first lecture, remember I used the example where we might have Emacs and GCC running on our system, and when one of them is waiting on user input, the other could be doing a computation, could be compiling your code. Similarly, the same thing can happen within a single program. So this is really common in server applications. So here I have a pseudocode for a web server where one thread is accepting connections, taking in new clients that are coming in, and then creating separate client threads that are going to service that client. When one of the client threads is waiting for the client to respond, other client threads can process requests that have already been made. Most operating system kernels also have threads internally as well. Typically, we have at least one kernel thread for every process, and usually one kernel thread for every user-level thread. But the kernel might also have other threads in the background to help it complete various tasks and to support all the different abstractions needed by the user. So here we have the basics POSIX thread API. The basic API consists of 4 calls, and you're going to use these in your assignment 1. The first call is pthread create. And what it does is it creates a new thread. It'll return the thread identifier inside of this variable thr. It allows you to specify some optional attributes, which most of the time, for your purposes, they will be null. And it lets you pass in a function that you would like to execute in this new context. That function is going to be executed in parallel with the current thread and with any other threads in the current process. And finally, you get to specify one argument that you'll pass to this thread. And it's a void star, so it's a pointer to an arbitrary region of memory. You can destroy threads the same way that you normally use exit to exit a process. You can exit an individual thread by calling pthread exit. And here, again, we use void stars to allow us to pass return values that could be pointers to structs or other fields. Pthread join, which is the same parallel to wait PID in the process abstraction, it lets us wait on a specific thread and receive the return value from that thread. And finally, pthread yield. pthread yield tells the operating system that we're ready to run a different thread or another process. It allows the operating system to put this thread to sleep, and the thread will not be executing for some amount of time while other threads will have a chance to work. A reason you might call this is that you're waiting on I/O. This might not be the best reason, but when you're waiting on I/O, you could call pthread yield to allow other threads to run while you have nothing to do. There's a lot of additional APIs that are available for synchronization and communication between threads, which we'll get to starting with next lecture. There are two main ways we can implement threads. The first method, which is the most common, is to use kernel threads. So the way that kernel threads work is that we implement the pthread create call that I described earlier as a system call. And what it does is internally in the operating system extends the process with a new thread with its own stack, with its own CPU registers. It sets it up and it creates its own kernel thread inside of the operating system to match, and the operating system is responsible for deciding which threads are going to run when. And there's this one-to-one mapping between user space threads and kernel threads. This is going to be a lot faster and lighter weight than a process, but it's still relatively heavy weight compared to other approaches. The main limitation here is that we have to go through the kernel. Every time we create, exit, join, or synchronize in any way, we're going to make a system call. And remember that a system call is this special function call that is hardware supported. And typically, it's going to be 10 times to 100 times slower than if it was implemented in the kernel. In practice, this is actually even worse. So those of you might remember the Spectre and Meltdown attacks that were attacks on problems with the hardware. And to mitigate these attacks, operating systems had to jump through special hoops to try to hide memory from the application to ensure that the processor's features couldn't be bent to read memory that they weren't supposed to read. In order to implement these mitigations, we've had to have slower transitions between the application, the user space, and the kernel. Second, these implementations have to be general. They have to please all the different users out there. So we're going to pay a price for all the features that we don't necessarily need, and we might lose the ability to do something specialized that might be better for our purposes. And lastly, these tend to be very heavyweight in terms of memory requirements. Every time we'd call pthread create, on most systems, we allocate a 2 megabyte stack. That's 2 megabytes of memory times the number of threads that you have in your system. To solve these problems, for certain systems, we can use an alternative approach, which is user-level threading. In user-level threading, we're going to have a single kernel thread or a single process, and we're going to run a bunch of user threads inside of that same process, that same kernel thread. Here, pthread create, exit, and all of their operations are implemented as library calls. Essentially, we never have to do a system call for all of these operations. To implement user-level threads, what we can do is we can implement all of these pthread functions I described earlier. Pthread create is going to allocate a little bit of memory for the stack. It's going to keep a list of all the threads that are currently runnable, that is, threads that are not waiting on I/O and not asleep for any other reason. And we're going to replace all blocking system calls like read and write. Normally, if you call read, your thread will go to sleep waiting for that read to complete. We're going to convert them into non-blocking versions. When we see that a system call is going to block, we make the call asynchronously, asking the OS to do the read for us, and we allow a different user thread to proceed. The scheduler can be implemented in user space, And the scheduler is going to run periodically and switch between different threads. If we want to implement preemption, we can use calls like setItimer to allow us to receive a callback from the operating system asking us to perform a task, and in this case to switch threads. We'll see how signals exactly work later, but essentially it's an API that allows us to register a function with the kernel that we're going to run. We can see a simple example of how we might do this with a multi-threaded web server. Every time the thread calls read to get some data from the browser, well, the read function is going to be put in a non-blocking mode. So it's going to read, it's going to return back saying that there's no data available, and then we're going to run another thread. And periodically, we're going to check whether or not there's any data available in that connection, and when there is, we can resume that thread and allow it to continue running. User-level threads have multiple limitations. The main one being that we can't take advantage of multiple CPUs or cores in our system. So if you have multiple CPUs or cores, with user-level threading, your program wouldn't run any faster, and you would have to use multiple processes. The other limitations are around causes of blocking all threads in the system. So you can easily replace system calls like read for a network I/O, but many operating systems don't allow you to do this for reading disk I/O, or for other special system calls that you'll have to somehow emulate or tolerate that all threads might be blocked. A second reason is that page faults can block all threads. So we'll get to see this in future lectures, but if we don't have enough memory in our system, we're going to have to hide that fact by moving memory in and out of your disk. And while you're waiting to support this feature, by servicing the request from the disk, you're going to have to pause the entire application. There's no real way to communicate this information to the application. Also, there's a possible deadlocks. If threads block on one another, we might not be able to make any forward progress. We'll see more about deadlocks in the future lectures when we talk about synchronization. So there is a solution to this, which is that we can do what's called end-to-end threading. And we'll see a really great example of this when we talk about the Go programming language. In end-to-end threading, we're going to have a set of kernel threads, and each of those kernel threads will be running one or more user threads. We can create more kernel threads as needed, but typically we'll use one kernel thread per CPU core, and then pthread, all the pthread operations that we described, will be running inside of this user-level library, and then the scheduler that's running on each of these threads will decide which of these user-level threads could run. This is an idea that's been done in a few places, and we'll see this with the example of Go in a few slides. But typically this has had a few problems. The main being that it has a lot of the same problems of user-level threading. Blocks, various causes of deadlock, and other things can be very tough to deal with. It's also hard to keep the same number of kernel threads as available CPU. The kernel knows how many CPUs are available, so your library will have to be aware of that. And the kernel also knows when things are blocked, and we may not know which threads are blocked. So we'll have to try to build some model of what the kernel's doing and replicate a lot of that state, which can get very complicated. So a user-level scheduler will have to understand all of these things and decide which threads are blocked. One of the ways we could do this is by extending the system call API, by building a way for us to communicate with the OS what information is necessary for deciding what user-level thread should be run. So the main lessons to take away is that threads if they're implemented as a library, can benefit from a lot of things. When we talk about synchronization in future lectures, all of those operations can be done so fast if they're done in user space, but they're not as fast if they're done through the kernel. A way to deal with this is try to use end-to-end threading. And there have been a few proposals for this, the main one being scheduler activations, that allows you to implement end-to-end threading correctly and work around all of those issues that we described. This shouldn't dissuade you from using threads. In fact, most of your programs should be multi-threaded if your goal is to achieve good performance and use all of the available hardware. For most purposes, you're going to want to have n threads matching the number of CPUs for n CPUs to maximize the use of the hardware. And if you want to achieve concurrency with I/O operations, you'll probably need more threads than that. We'll talk more in depth about this in the concurrency and synchronization lectures in the next few lectures. So before we continue on talking with OS 161 and looking at how threads are implemented, I wanted to briefly look at a case study of how user-level threading, or end-to-end specifically user-level threading, is used in the Go programming language. The Go programming language introduces this idea of a Go routine. This is a variation of the coroutine abstraction that other programming languages have. Go routines are incredibly lightweight user space threads. It's practical to have hundreds of thousands of Go routines running in the system because of just how efficient and lightweight these threads are. The implementation is pretty complicated and depends on a lot of features that the Go runtime provides. The compiler allows applications to use what's called stack segmentation, helps with preemption and garbage collection all at the same time. And the application threads, the Go routines, are running on this segmented stack. And what that means is that the stack is allocated in really small chunks. When we run a normal pthread creation, we use about 2 megabytes of fixed stack space on each thread. In contrast, the Go routines allocate small fragments of the stack, and they'll ask for more stack space as needed because the compiler adds instrumentation to detect when a particular function call might run out of stack space. Go routines use the end-to-end model, as I mentioned. They're built on top of kernel threads. And this allows them to achieve good multi-core scalability and efficiently use user-level threading. Here they create one pthread roughly per core. They'll create a few special ones in the background for I/O. And this is going to support many, many user-level threads, almost as many as you'd like. Go is uniquely positioned to solve a lot of the problems, even with end-to-end kernel thread models. It still could benefit from scheduler activations, but it's uniquely positioned because it's customized almost the entire stack. It has its own compiler, its own runtime that doesn't depend on the typical libc runtime of normal POSIX systems, and it's defined its own language to help them take advantage of all of these features. Each kernel thread that's created by the Go runtime is set up to run on a different CPU and will search in its own scheduler for what Go routine it can run next. Every logical core will be owned by one of these special kernel threads. It'll attempt to decide which logical core it's running on, and then it'll try to schedule Go routines on it. Whenever you make a blocking system call, those system calls, as we mentioned with other user-level threading packages, will be converted to non-blocking calls when possible. This is going to allow the runtime to yield the CPU to another core while a dedicated CPU pulls on kernel events using one of the event APIs provided by modern OSs, which maybe we'll get to later in the term. And it's going to see what events have completed to then reschedule any go routines that are need to run. And finally, for blocking system calls that we can't avoid, their solution to this is to release the logical core ownership on that kernel thread, allow the kernel thread to make a blocking system call, and then regain ownership of the logical core when they're done to resume that go routine. Or they can release that go routine back into the pool and allow another logical core to take it and run it. The other really neat feature that Go introduces is this idea of Go channels. And Go routines are meant to work really well with Go channels. And we'll see a little bit about this when we talk about synchronization. But the idea is to allow threads or Go routines to communicate through this mechanism, through this feature called channels. And the channels are denoted by the arrow operator that we see here. So I can create a channel. I can then spawn a Go routine using this nice syntax that they've introduced, where I can just say Go worker. And then I can wait for that Go routine to complete by using arrow done to wait for a result coming out of the done channel. The worker thread, once it's done some computation, can then return a value through the done channel to notify the main thread that it's completed. This is sort of equivalent to using it for join and for pthread. This is equivalent to using pthread join and pthread exit in the way that I've used it here to communicate a value. But it's broader than that because these threads could use this to communicate work to be done and load balance it across all the Go routines in the system. So let's briefly look at how kernel threads in OS 161 are implemented. And this is a good proxy for understanding threads in any system. But before we do that, we're going to first recap how the calling convention is implemented in the MIPS processor. This is how function calls call one another. The calling convention is the definition of how a function calls another function to communicate arguments, borrow registers for computation, and return values. One more important thing to remember is that all threads have their own stack. The stack is a region of memory where we're going to be able to save temporary state that are used by all of the functions. The stack will grow down in what we call stack frames, where each stack frame is corresponding to a particular function. So here, I'm showing you two stack frames, two halves of a stack frame, really. The first half here on the diagram is a call, has the arguments of the call are placed on the stack, the return address, and what's known as the frame pointer that we'll see in a minute. And the second function is the function that was called, and all of the state that was saved by that function, and all of its extra local variables that it couldn't fit in the registers. As I said, the calling convention defines how registers are used and how the stack is laid out. The registers are going to be defined into two groups: the caller saved registers and the callee saved registers. The caller saved registers in MIPS, they're known as T0 through T9, where the letter T corresponds to temporary, and the callee saved registers that have to be restored back when a function returns, known as S0 through S7, and the frame pointer, which is sometimes referred to as S8. When a function calls another function, the caller of the function is responsible for saving any of the temporary registers that it wants to keep. The callee, the function that is called, is responsible for saving any of the saved registers, the S registers, and the frame pointer. The function, each function is able to use all of these registers, the T and the S registers, to store local values. If local values don't fit in all the registers that we have at our disposal, we can place the remaining local values on the stack itself after all the other state of the stack. When a function calls another function, it's going to place all of its arguments into A0 through A3. There's only 4 arguments. If we have more arguments than that, the remaining arguments will be placed on the stack. As soon as that's done, that function can now call the new function and save the return address on the stack. It will then also save the frame pointer, and we'll see what the frame pointer is, and we'll set the frame pointer to this point in the stack. So we've grown halfway through the stack that I'm showing in this diagram. The frame pointer is a way for us to easily see each frame of the stack. It points to the boundary between the caller and the callee in the stack. Next, the callee decides what registers it needs to save. The compiler has decided ahead of time based on its register use, and will save these registers after the frame pointer. Any remaining local variables and temporary storage that is required will be placed after that, and the stack pointer will be pointing to the bottom of all of this. When a function returns, it typically returns the return value through 2 registers, V0 and V1. Remember that the stack pointer will always point to the bottom of the stack so that we have a well-defined point where the stack grows from. And the frame pointer will allow us to quickly unroll the stack by restoring the stack pointer to be the frame pointer and then returning to the previous function. This is really helpful for debugging because you can easily walk up all of the stack frames by just looking at the frame pointer and seeing what the old frame pointer value was and going to the next frame again and again until you've reached the top of the stack. So let's put all of this together. When we make a call, the caller is going to save all the caller save registers. We call a function. In this example, we're calling a function foo. We then save all of the used callee registers that we need. Foo then does its computation and then can restore all of these callee registers. Then it can return back to the caller. It places its return values in the registers and then jumps to the program counter where the program had just left off, right after the call instruction. The code there should restore all of the caller registers, and then it can continue doing its computation and using any results from foo. So let's briefly just look how threads and procedures or functions differ from each other. Threads, remember, can be resumed out of order, and a thread could call one or more functions, and we could continually call functions just in this stack-oriented way, this last in, first out stack, from each thread. Threads aren't going to switch as often, right? Procedure calls tend to be very short, but threads are going to run long-running computations typically. And threads can be involuntarily interrupted, right? We might have the operating system save all the state and switch to another thread or another process even, while a function doesn't actually do this typically. Let's put all of this together to see how threads are implemented in OS 161. OS 161 supports fork, exec, exit, and wait for processes, and you're going to implement some of these functions in assignments 2A and 2B. But OS 161 only allows you to have one thread per process. Where threads come into play is in the kernel itself. OS 161 supports kernel threads. It doesn't have any user-level threading, so you can't use pthread functions, and that's why we implement assignment 1 in user space on a Linux system. Kernel threads in OS 161 can be created in a very similar way to pthread create, but we're going to use a function called thread fork. Thread fork allows you to specify a name, which is really just there for debugging to make your life easier, a process that thread should be associated with. Threads can be created on behalf of processes, so they still are associated to processes, and a function that we want to enter into, and then we allow two arguments to be passed in. One is a void star, similar to the way that we pass in arguments in pthread create, and the other is a long, an unsigned long. Now I want to quickly point out that this is a really bad naming scheme. This is not fork. This doesn't duplicate the operating system. It doesn't duplicate anything. It actually is creating a thread. It really is pthread create. It should have been called thread create. But for whatever reason, the original authors of OS 161 decided calling this thread fork, most likely because it was used for the fork system call itself, to create the new thread, the kernel thread, belonging to the process when new processes are created. So we're not going to go into too much detail right now about all the different ways we can enter, but there are two main mechanisms that threads can be switched inside of OS 161. At the core, all of the threads go through the same set of functions, thread switch, which then calls a special assembly function that we'll see in the next slide, called switchframe switch. So the two ways that we can switch between threads in OS 161 is that we could call thread yield. Internally, the kernel calls thread yield for various reasons to allow another thread to run, which directly calls thread switch, that chooses a thread to run, and then switchframe switch that actually does the swapping from one thread to the other. And what this main function is doing here, it's actually switching the stacks. Inside of the kernel, we have separate stacks and separate register state for each thread. We're going to save the important state that we need when we call switchframe switch the stack pointer to point to the new stack, and resume and restore all of the state from the previous thread that we now want to run next. The second way that we can end up in this same code path is through a hardware interrupt. We'll talk about hardware interrupts more when we talk about I/O and devices, but the basic idea here is that a hardware interrupt will trap to the operating system and give the operating system control of the system. The hardware will place basic information in the CPU registers, and the operating system will create what's called a trap frame that describes the state of the CPU before the trap. It'll then call the function trap that'll actually decide what to do based on the type and cause of this trap, which typically will lead to an interrupt handler that processes the per device information, the scheduler, if it happens to be a timer interrupt, which then can call thread yield and thread switch into switchframe switch again. So if we understand thread switchframe switch, we'll basically understand how the core nugget of threads are implemented. And switchframe switch comes into two pieces. First, it saves the original thread. It then swaps to the new thread and then restores that new thread that it wants to execute. And the way that we do this is that we're going to add to the stack pointer a negative value. So we're allocating space for 10 registers to be saved. We're going to save all of the registers and any other special variables that we have. The global GP here stands for the global pointer, the return address, and all of the saved registers are going to be saved on the stack. And then we can actually swap from one stack to the other. Inside of A0 and A1, in the call to this function, we've specified the address of the old thread stack and the new thread stack. And it points to a structure on the stack that we call the switch frame, which is just this set of registers that we're saving and restoring. The second half of switch frame switch is the mirror of what we just saw. It's just restoring all of the state. It loads the stack pointer from A1, which remember is pointing to the top of this special structure. And then it has a NOP here. We'll get back to what this is in a second. And then it's going to load all of the saved registers, the global pointer GP and the return address RA, back from this special structure. And then it's going to have another one of these NOPs. It's going to then jump into the return address, and we can see that we have an instruction after this. So what's going on here? Well, these NOPs and that special add-I are in what's called the delay slots. So if you can recall, the MIPS architecture is kind of interesting in that it exposes some of the architectural complexity to the developer. It assumes that the compiler is going to be able to find interesting work to do when it's waiting for particular values to propagate inside of the processor's hardware. And these are called delay slots. So when you assign the stack pointer with a load from A1, it takes time for that load to be serviced. So you can't immediately execute another instruction that uses the stack pointer because that value needs a few cycles to load. So in the MIPS architecture, they specify one instruction in between that's called the delay slot, where they're not going to allow the SP value to be correct at that point in time. So we delay by one slot by inserting a no operation, and then we can then use the SP register. And the same thing is happening again. Later, when we see the next delay slot and we have another NOP, again, the hardware's not ready. It wants you to wait one cycle to load the return address before using the return address for anything. And here, the jump jumps into the return address after. And again, for jumps, there are also a delay slot. There are a bunch of places when you look at assembly for MIPS that you'll see delay slots being used, and you have to reference the architecture specification to know where all these places are. The second common one is after a jump. So when a jump to the return address is made, it takes time for the processor to realize that this is a jump instruction that it's processing and what the value of the target of that jump is. So it inserts one delay slot that allows us to insert an instruction here that's restoring the stack by adding 40 bytes, unwinding the stack to the caller stack frame. A second thing I wanted to note is that this next delay slot here, this last delay slot that we have a NOP, right after we load the return address, we could actually avoid this. If we placed that instruction one line above before loading the global pointer, today we briefly saw the thread abstraction. A process, remember, is an instance of a running program, and a thread is an execution context within that process, allowing multiple threads of execution to each share memory with each other, to share file descriptors and code. We saw how there are different versions of this can be implemented, the most common being kernel threads, but also user-level threading and hybrid end-to-end threading like Go routines. And we saw briefly how we save and restore the state based on the calling convention to allow us to switch from one thread to another. In the next lecture, we're going to get to talk about synchronization and see how we can communicate and synchronize between the threads to accomplish various tasks. This is going to introduce locks, semaphores, condition variables, and many new simple abstractions that allow communication between threads.